talk. I'll be talking about locally testable and locally correctable codes, and this is joint work with Sivaka and Gopi, who's around at Princeton, Swastik, Kopati, Rafael Oliveira, who was here till not very long ago, and Noga, who was also here as a postdoc a couple of years ago. So I'll be talking about error correcting codes, which are very efficient in the following sense. They have low redundancy, they are robust to a large fraction of errors, and they also admit very efficient detection and correction algorithms. So let me just introduce what these are, though I guess most of you are already familiar with it. We'll think of a code, we'll work mostly over the binary alphabet, and a code is just a subset of 0, 1 to the n. So it's just a subset, and we'll use the Hamming metric as a distance metric between any two code words. The rate r is a constant such that the size of the code is 2 to the r times n. So it's a measure of the redundancy of the code word. The closer r is to 1, the denser the code is, the larger the size of the code is. So ideally r should be as large as possible, as close to 1 as possible. The distance of the code is a constant delta such that any two code words differ in at least delta fraction of coordinates. And if you have a code of distance delta, this implies that you can correct up to delta over 2 fraction errors in a code word. So for instance, if you start with a code word C and you have a delta over 2 fraction, up to a delta over 2 fraction errors, and you get a received word R, then when you search in a ball of radius delta over 2 around R, there'll be only one code word in that ball, and so you can uniquely identify the code word which would have resulted in R. So the larger delta is, the more errors you can correct from. And a big open question is, what's the best trade-off between rate and distance? For every rate r, what's the best delta you can achieve? And for binary codes, we still don't know the answer to this question. So let me say what is known. So we know that we have constructions of codes where r can equal 1 minus h of delta. H is the binary entropy function. So that's this lower line. So we know that there exists codes with r equaling 1 minus h of delta. We don't know if this is optimal. We don't know if you can get codes which do better than 1 minus h of delta. There's an upper bound. The linear programming bound gives an upper bound. We know we can't do better than the bound given by that, but between these two curves, we don't really know what the right answer is. Okay, so the Gilbert-Varshamov says more about this GV bound. So there exists codes with such large rate, and in fact we know many constructions of codes which meet the GV bound. We know there's the random code meets the GV bound, a random linear code meets the GV bound, the greedy code where you just pick points greedily so that the distance stays large, that meets the GV bound. We know lots and lots of codes, but we still don't know if we can do better than the GV bound. And two very important and open questions in coding theory is, one is the GV bound tight. And this is again a purely combinatorial question because nothing algorithmic about it. Can you pack more points into 0, 1 to the n with a better rate versus distance trade-off? And another open question is, though we know so many constructions of codes meeting the GV bound, none of these constructions are explicit. So they are either randomized or they take more than polynomial time to construct. So the algorithmic question of giving explicit codes which meet the GV bound, that is still open. Very recently, Amno and Tashma came up with a really beautiful work which almost resolved this by giving explicit codes near the GV bound in some setting of parameters.
I should advertise it here in January for 2 weeks, and we'll talk about it.
So really beautiful work, and everyone should go for that. So this is all over the binary alphabet. If you look over larger alphabets, we understand the rate distance trade-off much better. Over large alphabets, the rate can equal 1 minus delta. This is the best upper bound and a lower bound. So this is the best you can do, and you can in fact achieve r equal to 1 minus delta over large alphabets. This is the singleton bound, and over large alphabets we understand this completely.
How large is bound?
So if you want to just approach 1 minus delta, if you want to come epsilon close to this, then I think you can get a large constant depending on epsilon. But if you want to, I think, equal it, then you need super constant alphabet size.
All your codes are
N
linear,
probably,
right?
yes.
All your codes are linear or not?
No, so far nothing needed to be linear.
The bounds are also for arbitrary codes?
Arbitrary codes, yes. Good. So the basic tasks associated with the codes, that the basic algorithmic tasks we are interested in is one is the encoding. So if your code was just a subset of 0, 1 to the n, then you would ideally like to you be able to use it. We would like it to come with an efficient encoding function. So give it a message how to encode it into a code word. And then there's a problem of testing and decoding. Testing is a problem of given access to a received word, decide if it's a true code word or not. And decoding is given a corrupted code word, recover the original underlying code word or the message that it came from. And these are all extremely well studied questions. We know codes with very good rate distance trade-offs, very efficient encoding, testing, decoding, running in linear or near linear time. But the focus of this talk is going to be on codes which support local algorithms, so local codes. So this was a question that coding theorists didn't study for a very long time, but in the 90s, part of complexity theory and proof checking, questions about codes which had never been studied in the coding theory context arose, which have now been studied extensively for their own sake. What can we do with codes in sublinear time? And with a sublinear number of queries into this a code word or a corrupted code word, what information can we get about the underlying code itself? So let me introduce what these notions are. So the problems we care about most are local testing and local correcting. Local testing is the problem of given a string r in 0, 1 to the n, distinguish between the two cases. R is a true code word and r is epsilon far from a true code word. And by just making a few queries into the corrupted code word, can we distinguish between these two cases? The problem of local correcting is given a received word r or a string in 0, 1 to the n. Suppose you know that it is close to a true code word. It's not too far away. So it's epsilon close to a true code word. So it arose after making not too many errors. Can we make for any coordinate j, can we find the true value of the jth coordinate by making few queries into the code word, into this corrupted word? You can't hope to recover in sublinear time, you can't hope to recover the entire true code word because you only have sublinear time. But for any coordinate, you could hope to be able to receive it, to recover it very efficiently. And you want to do this with few queries, and we'll always assume that the distance of the code is at least a constant, and so epsilon, let's think of to be some small absolute constant in both these problems. So just a cartoon picture, a received word is a corrupted code word. Locally testable codes, you want to decide is R in the code or not. A local tester is an algorithm which will go query the code in very few locations and output accept or reject. If it's a true code word, we want to always accept. If it's far from a code word, we want to reject with high probability. And a locally correctable code is given a string r which is not too far from the code. Given a coordinate I, the local corrector will make few queries and output the value of ci. And this should be correct with high probability for every I.
C is supposed to be one of the code word which is epsilon and close to r.
Right. So let's assume the distance is at least 2 epsilon, then there'll be a unique code word which is epsilon close to r, and then there won't be any confusion. Yeah. So here's an example, and this is probably the best understood example of a local code. These are the Reedmuller codes. So the codes are basically multivariate polynomial evaluation codes. You view the message as a polynomial, as maybe there's a string of coefficients of a low degree polynomial. The code word is you take this polynomial and you evaluate it on all of fq to the whatever underlying dimension is. If it's with a 5-variate polynomial, you evaluate this 5-variate polynomial in all of fq to the 5. And these codes, the right setting of parameters, you can get constant rate, constant distance, and these are testable with n to the epsilon query complexity. So let epsilon be fix epsilon to be whatever small constant you want. You can get codes which are testable with n to the epsilon queries, locally decodable or locally correctable with n to the epsilon queries, and also have constant rate and constant distance. And so I'll just say a few words about how you achieve this. We'll pick a large finite field, fq, and we interpret our message or our data as a polynomial of low degree, say 0.1q. And then the encoding is take this polynomial, evaluate it at each point of fq cross fq. Suppose we're just focusing on bivariate polynomials right now. Okay, so we take this polynomial, evaluate it at every single point. And now, if you just look at what the rate of this code is, so what's the length of the message compared to the length of the code word, you just do this, it's a simple calculation, the rate will be constant. The distance will be large, there will be at least 0.9, because since these polynomials are low degree and two low degree polynomials cannot agree at too many points, any two code words must differ on a large fraction of points. So this code has very large distance. And here's how you would locally test it or correct it. So here's the main idea, that if you take a low degree multivariate polynomial and you look at the polynomial restricted to any line, it looks like a low degree univariate polynomial. And so this is the main observation, and the local testing algorithm just does the following. You pick a random line, you query the points on the line and check that the values on the line look like a low degree univariate polynomial. And if it is, you accept, otherwise you reject. And the analysis requires several ideas, and there's been lots of work on getting a full understanding of this local testing algorithm, but it works. This is Rubenfeld-Sodan gave the first algorithm, and then there have been many other algorithms, many other papers or works analyzing it further and understanding it completely, but we understand it pretty well.
So here the number of queries is square root.
Yes, the number of queries we would make here would be good. You're querying a line. It's out of a two-dimensional space, you're querying a line. So if the code word had length n, this would be querying square root n locations. If you want to drive the query complexity further down, you can look at a trivariate polynomial, and then a line out of a three-dimensional space would be 1 over cube, would be a cube root of the total amount of information. And if you want the query complexity to be n to the epsilon, then you look at a 1 over epsilon dimensional space. How to do local correcting of this polynomial? If you want to, you have a corrupted code word and you want to recover the true value at any particular point a comma b. You pass a random line through that point and you query the values on that line. And if this received word didn't have too many errors, then when you look at a random line through a point, you won't see too many errors on the random line. And since the restriction of this polynomial to the line should look like a univariate polynomial, and now without too many errors on it, you can do univariate decoding to recover the true univariate polynomial on the line. And once you have the true univariate polynomial on the line, you can evaluate it at a comma b to find the value of the global polynomial on a comma b. And that's how you would do the local correcting of these polynomials. The query complexity for this two-dimensional space was order square root n, but you can drive it down by blowing up the dimension. Good. Good. So these are for local codes of constant rate. The Reedmuller codes were the best understood and the best studied. But in the last 5 or 6 years, there have been several other works improving upon these Reedmuller codes, and both in the testing regime and in the correcting regime. And I'll say a little bit about all of these works. All these works, so the Reedmuller codes, though they were efficiently testable and decodable, the rate and distance were both constant. The rate was actually degraded exponentially with epsilon. And all of these works improve upon the Reedmuller codes by making the rate not degrade exponentially with epsilon. You can get actually rate arbitrarily close to 1 and still achieve pretty much the rest of the parameters that Reedmuller codes got. So I'll say more about this. So what the plan of the talk is, I'll first survey some of these recent results on locally testable codes and correctable codes. And I didn't define what locally decodable codes are. They're a close variation of locally correctable codes. They're a weaker notion than locally correctable codes, at least when the underlying code is linear. And you are asked to recover only the message symbols instead of the true code word symbols. But let me not say too much about that. So I'll survey some of these earlier results, and then I'll talk after that about this work, which is we'll focus on codes over the 0-1 alphabet and ask, if you want local testing and local correction, what's the best possible rate distance trade-off you can achieve? So if you didn't care about local testing and correction, then the GV bound is the best possible rate distance trade-off we know how to achieve. What if you impose on top of that these codes need to be LTCs or LCCs? And what we show is that you can actually construct LTCs and LCCs also approaching the Gilbert-Varshamov bound, the GV bound, which is the best possible we can do, we know how to do in general.
Sorry, I missed what you said about the decodable. You said that LCC implies LTC?
LCC implies LDC for linear codes. For linear
You
codes.
just want to locally decode only a subset of the coordinates. This subset that corresponds to the original method.
No, I know what they are, I just didn't know if you're going to get the result from locally decoding also.
So LCC implies LDC because you can assume, you can take some subset of the coordinates and treat those as the message coordinates of the encoding
Because it's linear.
because it's linear.
So these are going to be
So and LCCs imply that you can recover every coordinate of the code word. For LDC, you just need to recover some subset of the coordinates of the code word, and that would suffice.
The number of queries here is some constant, right? It's polynomial number of queries.
But it doesn't matter, right? LCCs imply
I'm
LDCs.
just asking about
Yeah,
what's
this
the
Oh, right,
coordinate.
exactly.
It's not
So this new
surprising
result,
to think of, constant queries.
right, good. So this new result, when we talk about LTCs and LCCs, for now we'll just focus on little o n queries. What's the best query complexity we can also achieve for this result? And for now, even little o of n is interesting. You can talk about LDCs and LTCs and all these things with constant queries, or you can talk about like the regime we were talking about for Reedmuller codes, where we didn't talk about the constant query regime, but constant rate, constant distance, where we had many more queries. So let's think about anything non-trivial being interesting, and we'll see what we can do. Okay, so good. So there's a constant. So let's do the survey of what is known. And the constant query setting has been extensively studied. So you can look at Reedmuller codes in the constant query setting, and then there was the beautiful work of matching vector codes, and Zev is one of the co-authors on a beautiful sequence of works which achieve very non-trivial constant query LDCs. A lot of amazing results, upper bounds, lower bounds, and there's many basic questions which are open and we don't understand in this setting. Even for 3-query locally decodable or locally correctable codes, the best upper bounds and the best lower bounds are way off. So we understand the constant query. Though there have been a lot of beautiful works, there's still a lot left to be understood. But this is not what we're going to focus on. Let's talk about constant rate LCCs. So we want R to be a constant. So the code word length is only a constant factor larger than the message length. And Katz and Trevisan showed long time ago that if you want codes of constant rate, then you can't have constant query complexity. The query complexity needs to be at least log n. The Reedmuller codes we talked about, if you want n to the beta query complexity, then the rate decays exponentially in 1 over beta. But I did mention that since then, since the Reedmuller codes, in the last 5 or 6 years, there have been several works which go beyond the Reedmuller codes, and the kind of parameters they obtain is the following. You can get any r arbitrarily close to 1. So let pick r to be 1 minus epsilon, for epsilon being any tiny constant, and you can get query complexity n to the beta for beta being any tiny constant. So you can simultaneously get small query complexity of the form n to the beta and rate going close to 1, and these are locally correctable codes. You'll pay for in the what are you going to pay? As beta gets smaller and r gets closer to 1, you'll pay in the distance of the codes. The distance will still be a constant. It will depend on beta and how close the rate is to 1. But you can make the rate arbitrarily close to 1, and you can make the query complexity small. There are 3 very different families of codes which all achieve the same bound: multiplicity codes, lifted Reed-Solomon codes, and expander codes. Very recently, there was work with Swastik, Orr, and Noga, where we got codes again of high rate that were locally correctable from a constant fraction of errors with now n to the little o1 query complexity. So all the others had n to the beta query complexity for beta constant. Here you can get n to the little o1 query complexity, and this little n to the little o1 is some function which is super polylog, and sub polynomial is n to the root log n log n. That's the best we know how to do today. And one interesting and what will be also important for this work is that these codes over large alphabets also approach the singleton bound. So the singleton bound was the best possible rate distance trade-off that can be achieved. These codes which have this small query complexity over, you can get these codes for binary alphabet or for the large alphabet, and in the large alphabet setting they approach the singleton bound.
And large
A large constant. If you want this just to approach the singleton bound, then some large constant. Yeah. Let's see. Let me tell you what is known about locally testable codes. The Katz-Trevisan result analog is not known for LTCs. So it's conceivable that there are constant rate, constant query LTCs. In fact, 3 query LTCs of constant rate, these could exist. We don't know if this is true or not. The best construction we know for 3 queries has rate 1 over polylog n. But if you want to, let's fix the rate to be a constant and ask what is the best query complexity achievable. Then the Reedmuller codes, again, got rate degrading exponentially in 1 over beta with query complexity n to the beta. And then in the last few years, again, there was lots of works trying to go beyond these Reedmuller codes. And they also achieve similar parameters to what the analogous results for LCCs was, where we can get the rate being arbitrarily close to 1 and query complexity n to the beta for any small beta. It's very similar to the Reedmuller codes, and there are 2 families of works which do this, tensor codes and lifted Reed-Solomon codes. And then this other work, this recent work with, again, Swastik, Orr and Noga, we can get codes of high rate locally testable with n to the little o1 queries, and we get much improved query complexity in the LTC setting. We can get log n to the O of log n, so quasi-polynomial query complexity for LTCs. And again, over large alphabets, these codes approach the singleton bound. Okay, so we can get high rate and quasi-polylog query complexity for LTCs, and this is what is the best we know today. Yeah?
We have no reduction between one and the other, right?
No reduction. The proof technique I'll talk about is pretty similar, but we don't know how. We don't know LTCs. Neither one implies the other. These are just 2 different objects as far as we know.
Could you put on the one that before the Gemara and say that comparison?
That was 3 queries. That was constant queries, but then the rate was 1 over polylog. But if we make the rate constant, then the query complexity, now we can do polylog, basically.
There's no like trade-off between these, they're just sort of, they live on islands.
The proofs are completely different, so
But so your result only applies
could
in
be.
this regime, and their result only applies in that regime. Or
So I don't know if there's any interesting trade-off, at least. Maybe root log n both. I don't know if you've tried hard enough, and it's possible that one can do something. I'm not sure. But this is very 2 different, completely different proof techniques.
But don't the notes, for instance, Sudan, if you change so the way you presented it is the rate is 1 over polylog. But can't you make the rate constant and paint the queries?
Then I think
And it goes to what?
then n to the beta, it immediately goes to n to the beta. I think there's nothing in intermediate. Okay, so these were the 2 results for LCs and LCCs and LTCs, where you get n to the little o1 query complexity, and these codes approach the singleton bound. And I'll say a few words about the proofs of these results, because both these results will be many of these ideas or sort of these results will be ingredients to what will be the new work I'll be talking about. Okay, so how do you get these results? There will be both the LTC and the LCC proof. They have a similar high-level strategy, where so there are 2 components. In the first component, we'll try to get this reduced query complexity by going to codes of sub-constant distance. So up till now, we always wanted to focus on codes of constant distance and see what we can achieve. The first goal is let's loosen the distance. Let's take codes of sub-constant distance and then see if you can get improved query complexity. That will be how the first component is achieved, both for testing and correcting. And for the second component, we'll have a little gadget or a transformation which takes a code of bad distance and makes it a code of good distance without losing too much in testing and correcting. So it will be an operation which improves the distance. So at least for the LCCs, the first component where we want subpolynomial query complexity, but we don't mind losing in the distance, This is can be achieved by these multiplicity codes, one of the families of codes which went beyond Reedmuller codes. And I won't say too much about multiplicity codes, but these generalized Reedmuller codes, where instead of the Reedmuller codes were evaluations of polynomials, these multiplicity codes are evaluations of polynomials, and you write down the derivatives, the evaluations of the derivatives of the polynomials as well. And basically that's it. You take a polynomial, you evaluate you write the value and the value of all its derivatives, and then you look at what's the distance and the rate and all these trade-offs, and it's a calculation after that. And somehow the rate distance trade-off improves a lot by doing this, just by this operation of writing the derivatives. So on one hand, when you write derivatives, the code word is getting, the length of the code word is getting longer. So you're losing out in n, but you gain in the message length, because now you can take polynomials of higher degree than you could have otherwise to still get distance. And so you see what is the best degree of polynomial you can handle, and you do the trade-off, and you get much better. You get these codes have rate approaching 1. So we take these multiplicity codes, and these were the parameters. You can stretch k bits to just a little bit more than k bits, and you can get these codes are decodable in k to the epsilon time and queries. In the subconstant distance regime, if you don't care about the distance of these codes much, and so you only want to correct them from a tiny fraction of errors, this corresponds to codes of super constant dimension. These polynomials will be in super constantly many variables. That's what it will correspond to. These turn out to be decodable in a line is much tinier fraction of the whole space when the dimension blows up even more, and so you can decodable in much fewer queries. So you take this multiplicity code in this non-standard regime.
This is what we should remember, right? I mean the parameter. So this time and number of queries is what you're shooting for much better.
This is what we'll be shooting for.
And right now
the distance is bad.
It's roughly 1 over root log.
The query complexity is what we're also shooting for, but the distance is subconstant. We would rather have constant distance.
Everything here is efficient.
Everything is efficient. And the second component, this distance amplification component, is we'll use a very similar technique used by Alone, Edmonds, Luby, and then others. They use it in a very non-local setting. We're going to use it in an LCC setting in a different regime of parameters. But this operation is an amazing operation. We took these codes, which the multiplicity codes gave, and you apply this distance amplification, and as a result, you pay very little in the rate. This epsilon became 2 epsilon. We set epsilon to be epsilon over 2, and it all looks the same. The query complexity you also hardly paid in, and magically this distance, which was so small, became a constant. And these codes lay on the singleton bound, just by this distance amplification procedure. So it's a really amazing transformation you can apply to the code, which just blew up the distance, preserved the property of being locally correctable, and you paid just a little bit in the query complexity, and rate almost, you don't notice it in our setting of parameters. And so let me just describe what this transformation is to you. So you take your original multiplicity code word, which can tolerate only little o1 fraction errors. So it has little o1 distance, and you want to blow up the distance. You take this code word, you chop it up into pieces. You take each piece and encode it via Reed-Solomon code. This is the univariate analog of Reedmuller codes. So you just view the message as polynomials, and the code word is the evaluations of the polynomials at all your points. So you take each piece, you encode it via Reed-Solomon code, and then you scramble up the symbols using a good expander and block it up, and that's it. So so if your Reed-Solomon code had code word length, do I have notation? If your Reed-Solomon code word had code word length d, then you put a nice good d-regular expander graph you impose on it. You pass the symbols along the edges of the expander, and then on the other side you just collect all the symbols and block it up into one big alphabet symbol, and that's the description of this operation, which it's all linear. In this now, so this big alphabet, if you're going to block it up as a big alphabet symbol, then maybe you lose some linearity, because you take many symbols and you treat it as one, but then you can linearize it further by concatenating, by I mean, if you want to make it linear, you can make it linear by one more step of concatenation. In this big alphabet, in the final alphabet? Oh yeah, maybe it is linear in the big alphabet. Right. It is. It's not linear in this small original alphabet size you started, but in the final alphabet. You're right, it is linear. Yeah. So good. So it preserved linearity, at least over the big alphabet. And it had this amazing property of just blowing up the distance. So then and the proof is actually also very simple about why the distance got blown up. So since I think I have the time, let me say a few words about why this operation is so good. Okay, first for the simple case, let's suppose we want to decode. I want to show that this code, the multiplicity code word, you could only correct from a little over 1 fraction errors. Let me tell you why this code is correctable from a constant fraction errors. And now for simplicity, let's assume the fraction of you had a constant fraction of errors, but this fraction these errors were random. Then you don't even need this expander graph part. So let's just say the errors were delta over 2 minus epsilon fraction, random errors. Then these errors are all randomly placed. Then most of these gray blocks, these Reed-Solomon code words, let's think of D being super constant. So most of these gray blocks will have at most delta over 2 corruptions, right? If overall the number of corruptions is less than a fraction less than delta over 2, just by simple Chernoff bound, on a 1 minus little o1 fraction of the gray blocks will have less than delta over 2 errors. And whenever a gray block has less than delta over 2 errors, then you can decode the gray block to find the true underlying blue block. So now, 1 minus little o1 fraction of the blue blocks can be truly recovered. And if you can recover 1 minus little o1 fraction of the blue blocks, then now you only have little o1 fraction error left on the blue part, and so the multiplicity codes can handle it. And so you can decode the whole thing now from a constant fraction of errors.
You didn't use anything special to Reed-Solomon here, right?
Only the rate distance trade-off.
So in some
Nothing. Reed-Solomon was actually not necessary at all. It could be any good code.
the expander sort of allows you to behave as if the errors are random.
Exactly. So the part of the expander.
Yeah, it's a general phenomenon.
Right, exactly. Yes, exactly. So these random errors were like that. This whole decoding first observed that everything could have been done locally. So since everything was all local out here, we didn't lose much in the query complexity to do this two-step process. And now this expander, if you have adversarial errors, basically this expander and blocking is going to make the errors look pseudo-random. So if you have, so it's the same thing now. You take delta over 2 minus epsilon fraction. Suppose the number of errors is delta over 2 minus epsilon, and we have so many adversarial errors on the right hand side. Then by the expander mixing lemma, most of the gray blocks will have at most delta over 2 corrupt neighbors. And now proceed as before. So now all the gray blocks which have few corrupt neighbors, they can be correctly decoded to recover the blue blocks, and then once you have one little o1 error on the blue blocks, you can recover the multiplicity code word, and then that's it. And now you just set the parameters appropriately, and we get what we want.
This is the origin of expander. Von Neumann had this idea of correcting noisy circuits with random majorities, like duplicating every gate and then have random local majority networks to reduce the error. And Pinsker and others in Russia in the 70s were trying to make it explicit. And they realized that this is the kind of object you need, and then so Pinsker proved that a random one is, and then he asked Margulis if he has an explicit one, and Margulis expect the next day told him that using conjunct property you can get one, and that's how it got wrong.
So I just missed the parameters. So could you explain? Should you say again? So how big are the gray blocks?
We'll make the blue blocks be something like log n.
Log in.
The gray blocks will be some constant times log n.
So you don't need any kind of even special expander.
No special expander, yeah. And we know these are expanders because off-the-shelf expanders that can be used. And since these are all log n's, you'll pay in the query complexity only by polylog n, and so that all gets incorporated. It doesn't hurt the query complexity much in the setting of parameters we care about.
So it kind of turns out you could like you could take a fairly wide range of parameters and essentially
A
do
fairly
that.
wide range of parameters, yes, and this would still work. And then we also want this final code to be on the singleton bound, so the rate distance trade-off is optimal. And so if the multiplicity code didn't have to have good rate distance trade-off, but if you see what the rate and distance trade-off of this final code is, it's basically the underlying Reed-Solomon code. What rate distance trade-off that gets is basically what is going to be the rate distance trade-off of this final code. And so you can just observe that it's on the singleton bound, because you can correct from delta over 2 fraction errors almost. So the distance was almost delta. And what was delta? Delta was the distance of the Reed-Solomon code. The delta was the distance of the Reed-Solomon code, exactly. So whatever is the rate distance trade-off of the Reed-Solomon code is what is inherited by this final code.
So you get the locality of the multiplicity code.
Right. And the rate distance trade-off of the Reed-Solomon code. Assuming this multiplicity, we needed the multiplicity code to be high rate for the rate distance trade-off to be the same as that of the Reed-Solomon code. If the multiplicity code, if we started with Reedmuller codes, then we wouldn't get codes in the singleton bound, because we would pay in the rate. But since these codes are of rate approaching 1, yeah?
This looks very generally useful, because in doubly there is a lot of work on designing codes
Right.
which handle like this special random errors, like in electrical, like the electrical engineering perspective, they would have distributions on errors.
Right.
But this seems like you can somehow connect.
It's you, it's actually you.
Yeah. It's all local, and so that's
All the LDPC kind of codes are derived from the same place. Which one? The turbo codes are different. You are talking about tornado codes. Yeah, there are lots of T codes. Yeah, there's also the LDPC.
okay. So for LCCs, that basically completes what I wanted to say. LTCs, again, it's very simple. The component 1 changes. Here we use multiplicity codes for component 1 of LCCs. Component 1 will change for LTCs, but component 2, this error amplification, is exactly the same. And you just have to check that the testability also doesn't change. The property of being testable is preserved under this operation of blocking, etc. So component 1, we use tensor codes, and again in some non-standard parameter regime, achieves low distance and then efficient query complexity. So if you use the fact that tensor codes are locally testable in super constant dimension, then you can achieve actually the same query complexity that multiplicity codes got, 2 to the root log k log log k, where k is the message length. But I claimed you can do log k to the log log k query complexity. So actually much better than what these tensor codes achieve. So in this paper we also improved component 1 by alternating tensoring and distance amplification. You tensor, you amplify distance, you tensor, you lose distance, you amplify. So by some kind of alternation we can improve component 1 and then it feed into component 2 and get the quasi polylog. Okay, so
Do you think that the right answer is different for LTCs and LCCs?
So that's a good question. So now I don't really know what the right answer is, because before this work we really thought maybe the n to the epsilon was the right answer. 3 different works all getting the same answer. We really believe that should be the right answer, and this was quite surprising that you can get better, and probably neither of these is the right answer and you can do better. But I don't.
So there is a reason why you cannot apply the zigzag idea in the
Multiplicity
LCC?
codes. Yeah, I don't know. So since the multiplicity codes were the only starting point we knew for LCCs, the moment you try to go to query complexity, somehow that's some kind of threshold. The moment you go to query complexity, even if you don't care about the distance at all, and you're willing to degrade the distance completely, or you just have smooth codes, so 0 distance but still low correctable with few queries, that seems to be a bottleneck for multiplicity codes, because not only you need to query a line, you need to query many lines, and so if you reduce the blow up the dimension enough that the line becomes a small fraction, you'll pay for it in the fact that you have to query many lines and it blows up the query complexity for another reason,
Not the case for testing.
which is not the core case for testing. Yeah. So that was what I wanted to tell you about what we know so far. Now I'll tell you about the current work, which is, let's focus on the binary alphabet and let's ask if you want locality, then what's the best possible rate distance trade-off you can achieve. And we'll show that they're locally testable and correctable codes which approach the GV bound. So there's an asterisk, and I'll explain what it means. So this is the LTC result that we get is actually very clean and simple. So so this is what the theorem is. Pick any two constants R and delta, where the rate is just below the GV bound, so as close to the GV bound as you want. Then there is a family of codes with growing growing n with rate at least R, distance at least delta. So you can approach the GV bound and you get locality, local testability with the same query complexity as in the previous work. So the best possible local testability we know for high rate, and these also approach the GV bound.
So in the previous one, then, how big was the alphabet?
So the alpha, you can get that for all ranges of alphabet, for whatever the alphabet you want.
Smallest one.
Binary. You can get binary, but it won't be on the GV bound, the previous one. So the previous one you got singleton bound for large alphabets, but if you make it binary, so in the previous code you have to block up these, after you do the expandering, you have to block up big chunks of symbols and make it a new alphabet.
Yeah, you made it binary.
You can make it binary by further concatenating down, but that would lose the GV bound. The next step of concatenation would make you lose the, you'd pay something in the rate distance trade-off, and you wouldn't get the GV bound from that.
It's still constant rate, constant distance.
Still constant rate, constant distance.
So it's still pretty good. It's just
You would just you won't get the best possible rate distance trade-off, but you'll still get high rate. All the parameters will be the same if you don't, as long as you don't care about what the distance is as a function of the rate.
It's like, it's basically what happens to the Reed-Solomon code. That's the bottleneck right there. It's Reed-Solomon code is the best alpha that you want. But if you concatenate with a binary code,
Right.
you lose the
Right.
And then you get worthless.
Not the GV bound. You lose something. It'll work out. We can probably see, work out the parameters, but you lose something in the rate distance trade-off. You won't get entropy of delta, even if you concatenate with the best possible binary code.
There'll be a constant. I think.
There'll be a
It's one
constant.
of
There'll be a
the-
constant. You lose something in the constant in the distance or a constant in the rate. The LCC result we get is not as clean. So this is what the LCC, this is the best LCC statement we can get. Pick any delta which is super close to a half. Then we only talk about the GV bound for those kinds of deltas. So let rate be anything which is not up to 1 minus entropy of delta, but 0.99 close to what the GV bound is. Then you have a family of codes with code word length at least n, rate at least r, distance at least delta. And the query complexity is, we can correct from half fraction of errors, but the query complexity is some n to the epsilon. So n to the n to the 0.1, say. So you can't get what the multiplicity codes achieved, the earlier work which got 2 to the root log n log log n, we can't get such good query complexity. So we get worse query complexity. So again, that was the picture, the GV bound fourth picture. We only focus on the regime where delta is really close to a half. In that regime, you can make the rate go as close as you want to 1 minus entropy of delta, and you can make the query complexity be n to the epsilon. So these, I put fixed constants. You can get this for general epsilons and betas. So let's not, so let me tell you what you can do. You can make this query complexity to be any n to the epsilon. You can make this 0.9 however close to 1 as you want. But no matter what constant you pick here and what constant you pick here, the delta has to be close enough to half as a function of those two constants. So as long as delta is close enough to half, you can achieve n to the epsilon query complexity.
Rate will be meaningless, right? I mean, we're not really. It has to be.
No, you could have hoped for any rate. You could have, no.
Rate of delta in this regime is getting close to 1.
Right?
Yeah. Oh, I see.
No. We're talking of,
Delta in this regime gets close to 1.
right, so these codes have small rate. Right. But I'm saying this 0.99, how close how close you want. I mean, you could have had this statement with delta being anything, but right, and you could have hoped for the same statement. But this will only hold if you make this query complexity small enough and you want to be close enough to 1 minus entropy of delta, then delta needs to be close enough to half for our result to hold. And so this is saying the same thing. So let me tell you about the LTC result, because that is really clean. So here's a general thing we can prove. Suppose you have high rate LTCs with query complexity Q. So what we showed in the earlier work was high rate LTCs with query complexity quasi polylog n. Okay, but in general, if you have high rate LTCs with query complexity Q, we can construct LTCs on the GV bound with query complexity O of Q. This is something we know how to do. And on the GV bound, on any point of the GV bound, any point on the GV bound curve. So basically, if you have constant query LTCs of high rate, this would imply constant query LTCs on the GV bound. So this would be a general reduction. So if you believe that these don't exist, which then maybe one can do it by ruling out this implication that you can't get constant query LTCs on the GV bound. So this is the kind of reduction we will show. So here's the plan of what's coming up. I'll tell you about something called Thomason's theorem, which gives a way of a technique for constructing codes on the GV bound. And then I'll show you why this theorem and the previous result almost immediately implies the LTC result on the GV bound. And then we'll talk about how to get LCCs on the GV bound, and that needs several more ideas. In particular, we'll see a very beautiful scheme by Guruswamy, Indic and Sudan for decoding Thomason's codes and how you can use that in the local setting to get LCCs on the GV bound. So first for the let me tell you Thomason's theorem, because this is really the result we'll be using, and this is how we get codes. This gives a scheme for constructing codes on the GV bound. Basically, randomly concatenated codes meet the GV bound. So more precisely, this is the statement. You take any code over some large alphabet, which is on the singleton bound. So r plus delta equals 1. Like Reed-Solomon. Okay? So that the Reed-Solomon is an example of a code meeting the GV bound. Exactly. So that's the outer code. Now, this outer code, say it's of length n, then it has n symbols of a big alphabet written down on it. Each symbol you convert it to binary by applying a independent random linear map to it for each symbol. So there's not one linear map which will apply to all symbols to concatenate it. We'll take a different independently chosen random linear map per coordinate and do the concatenation coordinate by coordinate. So the first coordinate will have random linear map number 1, second coordinate will have random linear map number 2, and so on and so forth. So you will pick n independent random linear maps, apply it to each coordinate, and you get a binary code out of it. And this code is on the GV bound. So again, this was your outer code which met the singleton bound. You apply this, you're going to each alphabet symbol got blown up into a binary code word of this new random linear code, and you do it independently for each coordinate.
Constant expansion. What is the size of sigma relative to 2 to the t?
Good. So sigma versus t. So there's a big flexibility in Thomason's results. You could there's a big range of parameters for which t would work. In fact, if sigma is of size 2 to the t, then even codes of rate 1 would have sufficed here. We don't have to have any added distance into these codes. So there's a big range of parameters for which this would just work.
So it could be a permutation or something.
Could be a permutation, yes.
So why is it okay to use a random
It's not okay.
So it's not okay. So I said, so for the GV bound, so we don't know codes. So the question I said right in the beginning, we don't know explicit codes on the GV bound. Every construction of codes on the GV bound either need exponential time or need some randomness. And so these codes which we construct here also, which I'll talk about, these locally testable codes on the GV bound, are not going to be explicit codes. There'll be some randomness inside the code. I'll have a random procedure which generates a code which is locally testable. So
Still efficiently decodable.
still efficiently encodable, efficiently decodable. Everything is efficient about it, but it will only be a high probability guarantee because there'll be randomness.
You need a bound on t and sigma, right?
Right.
Logarithmic or something.
So t will be small, but
T is not a constant, right? Like T is going to grow with the dimension of the.
you can even take t to be a constant. Even if you take t to be a constant.
So what's the statement about?
So these codes are on the GV bound. These codes which you construct, you start with a code on the singleton bound, you do this operation, you get a code on the GV bound.
For this, you have to say something about t and sigma.
So I'm not setting all the parameters for simplicity, but I think t being, if sigma is 2 to the t, you can just take t to be that, and that will work. Permutation, and that will just work. And you could also take t to be larger. It wouldn't matter. It will still work. So here's how you get LTCs meeting the GV bound. We already got LTCs over large alphabet approaching the singleton bound. We considered that was what the previous word paper constructed. You take these LTCs, you concatenate them with random linear codes in each position. By Thomason's result, it will approach the GV bound. So these are not codes on the singleton bound. They're really close to the singleton bound. They approach it, and so you just check in Thomason's by going to the proof and make sure that these will approach the GV bound. And they do approach the GV bound. And this random concatenation procedure doesn't affect the local testability of the underlying code. So the query complexity blows up by a factor that is polynomial in t, where t was the block length of the inner code. So the tester of the final test, so this just gives you the locally testable codes on the GV bound. And the tester is, you run the tester for the outer code, the main code, the outer code, and then to convert it to a tester for the full code, you just run the test on the outer code, and whenever you have to query a symbol, you query the full, you query all the t locations of the corresponding code word, and then you check that it's a legal code word, invert it to find the message, and run the tester on the outer code word. If everything passes, you accept, otherwise you reject, and it's easy to see that it's a tester for this concatenated code. And this just gives you the LTCs on the GV bound. What goes wrong? Why can't you do the same thing for LCCs? So we also have LCCs approaching the singleton bound with good query complexity. We can again randomly concatenate each coordinate to get this binary alphabet, and the resulting code will again will approach the GV bound, just like before. So great, so we got codes on the GV bound. It's all still an LCC. All this random concatenation procedure won't change the LCC-ness. What we lose is that the fraction of errors we can correct from will not be delta over 2. It will be a code which lies on the GV bound. It will be locally correctable, but it won't be locally correctable from half the fraction of errors, half the distance. And if you're not locally correctable from half the distance, then what's the point of lying on the GV bound, right? The whole point of having codes for of large distance or great rate distance trade-off is that we can correct from a large fraction errors. So aesthetically, if we are not able to correct from delta over 2 fraction errors, I mean, it's kind of cheating. Yes, you got a code which is on the GV bound, which is locally correctable, but if it's locally correctable from much fewer errors than half the distance, then something feels not right.
And why is this? Why is what is that correction procedure usually? Where is the correction procedure?
So how would you have, so if you took this LCC, how would you correct it? You would first correct, you would run the correct on the outer thing, each correct have a symbol, you would read the whole thing, and locally then you would correct each inner code word. But if you have
you take a union bound on the errors for
right, you can corrupt too many, right. If you have delta over 2 fraction errors overall, you can corrupt a pretty large fraction of the inner code words, and so that when you pass it up to the outer code, the outer code wouldn't be able to handle those many errors.
You have to do that independently for each coordinate for everything to work.
Right. Right. But that's okay, you can do it independently, it's just that the fraction of errors you would tolerate won't be half the total final distance. You would be able to, maybe. But for this process, I think this, you need more just doing the naive decoding where you decode each inner symbol. Even if you don't care about local, even you just do it globally, even then, just the naive way of just doing, decode every inner thing and then go up and then decode the outer thing, it won't handle delta over 2 of the total fraction of errors.
So what will it be, delta over 4?
Probably delta over 4, you can probably do better than delta over 4. And something it's the Diablo of half what the Diablo of bound is, which is
You can't like concatenate with an expander or something to fix this issue, like somehow that worked before.
I don't know.
The question is, you have errors in this local decodings anyway, whether, even if the errors are distributed randomly, you have to.
Right.
But if they're distributed randomly, it seems like we're.
I don't know.
Okay, I'll tell you how we go around this problem. So this is the problem even for just unique decoding the Thomason code. How does one do it even without caring about locality? Just try to do the decoding. Just forget about LCCs. Just how do you decode these codes up to half the distance? So to even start talking about that, I'll introduce 2 more concepts. One is the notion of list decoding. So to list decode a code, you're given a received word R, and you're given a parameter rho, and say R is not within half the minimum distance to a true code word. If the received word is within half the minimum distance to a true code word, there's a unique code word which is half the minimum distance close to it. So if rho was delta over 2, then this is just unique decoding. What if rho is more than delta over 2? Then given a received word, there could be multiple code words which are rho close to your received word. And list decoding says just find all possible code words which are row close to your received word. And hopefully they're not, if you're in a setting where there are not too many, hopefully you can get away with it and do something with it still. And the Johnson bound, again, is the classic theorem bound for list decoding. And in this setting, when the code has distance half minus beta, think of beta to be some small constant, you can actually list decode from half minus square root beta fraction errors with small list size, constant list size. So qualitatively, if the distance is really close to half, for unique decoding you can only tolerate 1/4 errors. For list decoding you can tolerate almost up to half fraction errors. And what you'll output is a small list of possible code words. You can't uniquely recover what the true code word is, but it will be one of a small list. And so if the regime of focus where we are looking at delta being close to half, so delta over 2 would have been 1/4. You just want to correct from 1/4 errors, but the Johnson radius lets you talk about the errors being all the way up to half. So that was list decoding. There's another notion called list recovering, which will also be needed, which is you're given a code and you want to recover the code. So for each, so you're given the coordinates of your code word, and for each coordinate you're given a small set of symbols, SI. And the problem is find all code words which agree with these lists in most locations. So in most locations you want code words where CI belongs to the list SI. That's the problem of list recovering. So when the list sizes are exactly 1, that is exactly list decoding. List recovering is now you have these bigger lists on each, corresponding to each coordinate, and you want to find the code words agreeing with most of these lists. And in the setting where hopefully there are not too many such code words, you can hope to find them all. And you can do the list recovering problem also. So you have a small list of symbols on every coordinate. You want to find the code words which pass through most of these lists. So now let's forget the local codes. Let's just talk about how these Thomason codes, or you start with this code say the Reed-Solomon code, you concatenate it, how would you hope, with this Thomason scheme, how could you hope to even unique decode it up to half the minimum distance? So the naive way would be decode each inner code word, pass up the symbol to the outer code word and decode the outer code word, and this doesn't handle a good fraction of errors. The Guruswami Indik Sudan strategy for decoding these codes is the following, and it's a really beautiful strategy. That you can, though you just want to unique decode the full code, the final code, use list decoding for the inner codes. So you have your outer code, you take every symbol and you put this random linear map and you encode each symbol. When you want to decode the whole thing, you're going to decode every inner code word. Don't just decode it, list decode it. So now when you had a unique decoded, you could only handle half the distance. But when you want to list decode it, you can handle much larger fraction errors. So these inner code words had also distance about a half. To list decode it, you can tolerate half minus epsilon or half minus eta fraction errors. So then you list decode all these inner symbols and you get a small list of possible code words. So you pass on these small lists to the outer code, and now you list recover the outer code from a large fraction errors. And as long as this outer code is list recoverable, which it is because the rate distance trade-offs are so good, you can effectively decode this concatenated code from almost half fraction errors.
Does this cost you efficiency?
So we're not even trying local right now, we're trying global, and this is all polynomial time. Say the outer code is the Reed-Solomon code.
So you have to try like all possible.
Isn't it growing exponentially if you have a constant size list for each of?
So we know algorithms for list recovering the Reed-Solomon code efficiently. If you have small constant size lists everywhere on every symbol, we know that the global list size will be constant, and we have algorithms. The Guruswami Sudan algorithm for list decoding Reed-Solomon codes can also recover Reed-Solomon codes. So we are very efficient. At least when the outer code is a nice code like the Reed-Solomon code, we have efficient algorithms for doing it. So if you choose the code, at least the outer code cleverly, then you can do this efficiently. And you can go almost all, you will list recovery, you'll get up to half, you can recover up to half fraction errors. So as long as the inner code has distance close to a half and the outer code is L rho list recoverable, well L is some large constant and rho is close to 1, this scheme will work. And again, the Reed-Solomon code, and the appropriate Reed-Solomon code is the outer code, and inner codes of distance close to half just work. So that's the scheme. This was the global decoding scheme. We've lost LCC-ness in this combined scheme. How do we get locality out of it? So first is the picture of what happened. We had the outer code word. We concatenated each symbol with this to get a binary out. Each symbol was with an independent random code. We concatenated and got this big binary code word. Now this binary code word got corrupted in a large fraction of coordinates, and we still want to be able to find what the original message or the original code word is. So we list decode this corrupted code word on every block and get a small list of symbols on the outer code word, and I need to list recover this outer code word to get a small list of code words which could have corresponded to the true code word. And now if you want to just decode from half the minimum distance, only one of these could be, if you just want to unique decode up to half the minimum distance, at most one of these could be that close to your received word, and so by sampling you can tell which was the correct one and recover it. And if you wanted to list decode the whole thing, then you can recover this entire list. So that was the scheme. How do we now make this whole thing local? So we can take the outer code now to be over the large alphabet approaching the singleton bound, so that random concatenation would achieve the GV bound. and let's take a local, hopefully this code, let's start with an outer code which is a local code. We would need it to be something, we needed list recoverability in the earlier scheme. So we would need this outer code to be list recoverable in a local sense. So there's a notion of local list recoverability. That's what this outer code would, that's a property this outer code would need to have. It should be able to do this.
This was defined before?
This was defined before, it's been studied before already. So you need local list recoverable. It's like local list decodable, but for list recovering, it had been studied before. So you can, you need a notion of locally list recoverable. You would also need the outer code to be locally testable for the following reason. So this is just some technicality which comes up in locally list recovering. So what is local list recovering? You want to locally, so there's maybe a whole list of possible code words which agree with your the information you've given, and locally you want to recover all of these. So your local algorithm will produce the local algorithm will produce a bunch of black boxes corresponding to each of these code words, and each black box will correspond to a different code word, and it will make few queries to recover the corresponding coordinate for whichever underlying code you're trying to recover. But this scheme, most natural local list recovering schemes, when they produce these bunch of black boxes, some of these black boxes might have garbage output. So you know that all your true code words, some subset of the black boxes correspond to the true code words you're after, but some of these black boxes may output garbage. That is the way most natural local list recovering schemes work. And so you want to weed out this garbage, and you need local testability to weed out the garbage. To say that you only want to keep the black boxes which are true code words, discard the rest, and once we have black boxes which have only the true code words, then by sampling we can recover the unique one which is closest and keep that. But we needed local testability to weed out the bad black boxes. So we needed local list recoverability and local testability. These are the two properties we want the outer code to have, in addition to lying on the singleton bound. And so the problem is we don't know such codes which also lie on the singleton bound, also are locally list recoverable and are locally testable. So that's what, to make the scheme local, that's what breaks down.
Why doesn't list recoverability imply testability here?
Almost for this.
List is empty. I mean, can I just list recover?
How do you choose at the end the one you like? So you have local list recoverability.
Oh, I see.
But at the end you have to output one.
I see. So the radius for the local list recovery is going to be a little larger, and I want to find the guy who's closest.
Even without, so the local list recoverability will output some candidate code words, and some of them will be just not true code words at all.
Just by definition.
Just by the way the list recoverability, but with the definition of local list recoverability and the way these algorithms for local list recovering works, you basically get advice on some random point, and based on the advice you find all code words consistent with that advice, and if your advice is wrong advice, then you might output garbage. So you want to weed out those, and so local testability was also important, at least the way we thought about it. And so we don't know codes which are locally list recoverable, locally testable, and are on the GV bound, on the singleton bound. So here's something that would fix it. Let's not approach this singleton bound. We observe that even if you have some pretty decent rate distance trade-off, which is even not approaching the singleton bound, then if you do this random concatenation, you can get pretty close to the GV bound. That's where we lost the 0.99 in the first slide, where we don't approach the GV bound, but we get 0.99 close to the GV bound. That 0.99 comes if you start with an outer code which is not on the singleton bound, but just has pretty decent rate distance trade-off. So let's sacrifice on, we are able to sacrifice a little bit on the singleton bound and still get by. Good. So how do we get codes with pretty good rate distance trade-off, but are also locally testable and locally list recoverable? Those multiplicity codes, those earlier codes which I talked about, don't have these properties. So if you had locally testable, which came from the tensor codes, we don't get locally list recoverable, and the other way around too. How do we get locally list recoverable codes? We'll go back to the Reedmuller codes. okay, which is no derivatives, nothing. The basic Reedmuller codes, which were locally decodable, they turn out to be also locally list recoverable, and they are locally testable. So let's go back to the basic Reedmuller codes. They are locally testable. This is the original Rubel-Feld-Sudan local testing algorithm for them. These are locally testable. They are locally list recoverable. This follows from this Aurora Sudan and Sudan Trevisan Vadan algorithms for, I think they did it for local list decoding, but if you just go into the algorithm and you see that it also works for local list recovering. So it based on, again, you sample a random line, you list recover on the corresponding Reed-Solomon code in the random line, and you piece it all together. So you take these Reedmuller codes, and it turns out that these codes don't even have the good enough rate distance trade-off or the decent rate distance trade-off that we would need to plug it into the Thomason result. But you take these Reedmuller codes and you apply this AEL expander transformation on top of it. It will blow up the distance and make the rate distance trade-off good enough so that we can plug it into Thomason's concatenation to make it approach the GV bound. So that's basically the outline of how the proof will go. So I'll just summarize what this LCC part was. We take the Reedmuller codes. They're locally list recoverable and locally testable. You apply this AEL distance amplification procedure, then the rate distance trade-off improves, and it doesn't affect, you have to check, it doesn't affect the local testability that we have already claimed. It also doesn't affect local list recoverability. So that's good to know. Then you apply the Thomason construction where you concatenate each symbol with a random linear code, and then to decode it, each random linear code you would list decode to get the list of candidate symbols at each location. Then you would pass it up to get a list recovery problem on the Reedmuller cum AEL code, which is you can solve by doing list recoverability of the Reedmuller code. And then you would get a whole the list of candidate black boxes corresponding to these code words. Some of them may be garbage. You'll prune out the garbage by the local testability of the Reedmuller codes, and then identify the unique delta over 2 close code word by random sampling. So you need all these ingredients to get up to be able to correct up to half the minimum distance of the GV bound, the delta of delta. Good. So that finishes the description of the LCC. Let me just finish with some of the most interesting open questions. One is we have LCCs now with sub-polynomial query complexity. That's the KMRS result. But to make it to get LCCs on the GV bound, we lose in the query complexity. We can only do n to the epsilon query complexity. So can you get better improved query complexity for LCCs on the GV bound? Can you also do this for GV bound for all delta? For us right now, we need the delta to be really close to half to make the scheme work. So can you do it for other values of delta? Can you get LCCs on the GV bound for your delta not being close to half? And then just general and important questions. Can you get explicit codes meeting the GV bound, which again unknown gets it in some regime, almost solves it in some regime of parameters, but generally can you?
Does it get efficient decoding for it?
I think that, yeah. It seems to me
Probably.
that it does.
Maybe, I'm not sure. And is the GV bound tight, which is again a big open question. Can you do better than the GV bound? Okay, so thank you. Yeah.